Okay. Thank you very much for Dr. Pong's introduction and the invitation for me as a visiting lecturer at the UCL. I've been here for almost 1 month, and I still have another 1 precious month. I really love London and enjoy the lifestyle here, and hope I could stay more and share more experiences with you guys. And thank you very much for your attendance today to my seminar, and also say hello to those guys on Zoom. So today I'm Wei Lin. I'm from University of Technology, Sydney, Australia, and my university is located at the central Sydney, and hope that you guys will visit in the future. So today I would like to share some of our recent research about the advanced electromagnetics technologies, particularly for the wireless power transfer enabled Internet of Things ecosystem. So first, let's look at the so first is the outline of this talk. In the beginning, I will introduce the background of the advanced electromagnetics technologies for the WPT, so wireless power transfer, WPT for short, enabled, so IoT ecosystem. And then I will introduce our research works that in this application. Followed by that, I want to also introduce a little bit of my other research works in other applications to save our UCL colleagues. Maybe we could collaborate in some topics and some applications in the future. And last but not least is conclusion and some future perspective. First, I would like to introduce a little bit about the history of wireless power transfer. So the wireless power transfer actually categorized as 2 systems. So one is near-field inductive WPT. Okay? This technology has been commercialized already, so it's the products can be seen everywhere, and we have used them in our daily lives. So the scientific background is actually can date it back to the 2 gentlemen here. So first one is the French scientist Andrew Ampère. So he invented the Ampere's law. So from Ampere's law, we know that if we have a constant current, right, either flowing a straight line wire or flowing in a coil, it's gonna generate a magnetic field around it, right? So this is a classic Ampere's law. But Ampere's law tells the relation between the current and its magnetic field, right? Magnetic field. We have Ampere's law. This cannot make wireless power transfer happen. Only if we have another equation here invented from Michael Faraday. But Faraday actually a English. So he was born in London, not far from UCL. Like 5 years later, Faraday proposed the Faraday's law of induction. So which tells us if you have the time-varying magnetic field, this time-varying magnetic field will create an electromagnetic force, right? Electromagnetic force. So suppose if you have a primary coil that have the alternative current on it, if you have the secondary coil in the field, it's gonna copy the energy from the primary coil to the secondary coil. So Faraday's law actually tells the wireless power transfer via the magnetic field is feasible. Okay, it's feasible. But until recent 15 years, the technology has been commercialized. And I can say it's very successfully commercialized in many perspectives of life. So we have the wireless charger for the mobile phone, like this. This is a typical wireless charger product, and also for a smartphone or iPod. So The concept is just similar as Faraday's law. So you have the primary coil, we call it the charging coil. So you have alternating current on it. So it's going to induce a magnetic field. It's time-varying magnetic field. So if you place your secondary coil on top of the primary coil, the energy get coupled from the main source, okay, to the device and the charge. But the one problem of this technology is that it's very short distance. And also you have to place the axis of the two coils precisely. If you miss a little bit, so their co-axis, the charging will break up. Okay, so means that the distance is very limited. And this technology is also a mature technology. So you can easily buy a design module from Element 14 with only like 16 Australian dollar. So you can do some experiments and development based on the kit. It's very cheap. So it's a commercialized, successful commercial products. And also the standard for this technology is called the Qi standard. So it's developed in 2008. So one thing behind this, the story behind this is Qi. Why? You guys know why this standard is named as the Qi? It sounds like a Chinese character. And so Qi in Chinese is like a Kung Fu master, like Bruce Lee used the Qi. It's a very strong energy. So in the traditional Chinese Kung Fu. Qi Kung. Yeah, Qi. So this actually comes from the Chinese character Qi. So you cannot see it. So it's intangible, but it's very powerful. So it's very similar as what we have here, the volatile transfer. You cannot see it, but the energy is there. You can, transfer very high power to one source, okay, to another. So if you look at the product, if the product go to market, it has to have the Qi standard. So like this one, it have the Qi icon here, so means that it's already so all the specifications have been tested under the Qi standard. So you can look at it. So now we have already more than 3,700 Qi certified products online. So this is the near-field WPT. But the problem is, as I said before, it's very short distance, right? Very short distance while it's charging. Here we targeted on much long distance, even up more than like kilometers the distance while it's power transfer. So what makes this happening is the electromagnetics. We're going to use electromagnetic wave to do the far field while it's charging. So the scientific background of this technology can date back to another famous English man, James Maxwell, and he invented Maxwell equation. So predict existence of the electromagnetics. Okay, so Maxwell equations actually tells us the time-varying electric fields will induce the time-varying magnetic fields. And again, the time-varying magnetic fields will further induce the time-varying electric fields. So that's why the electromagnetic field is going to propagate from the source to the long distance, right? But propagate in the medium. But he predicted the existence of the electromagnetic waves. Only after, like 20 years later, so in 1887, Henry Hertz, his first time, used experiment device to detect electromagnetic waves to verify the existence of the EM wave. So what he used the actually it's a loop antenna. It's very simple loop antenna to pick up the spark, okay, the spark gap transmitter to pick up the electromagnetic wave transmitted from this spark gap and detect the existence of the electromagnetic wave. So these two guys, their work actually laid the foundation for the far field wireless power transfer using via the electromagnetic waves. So let's look at some engineering milestones on far-field WPT. So this guy is I can say is the father of the far-field WPT. So he's Wei Lin. He was working at the Rayson the company, and in 1964 he invented the device that is essential for the far-field WPT. That is a Rectenna. So Rectenna is actually an antenna integrated with the rectifier circuit. So the Rectenna can capture the electromagnetic wave and convert the electromagnetic wave into DC power and power up the following cascaded electronic device. So it's a Rectenna. So he first, in 1964, he did the demonstration of the wireless power, a Rectenna array, and it's connected with the helicopter fan. And he demonstrated that apart from almost 20 meters, he can use a dish antenna to wireless power this helicopter, okay, by the Rectenna array. So he's the first guy that made the wireless power transfer happening. So in 1964. And after that, a lot of activities and projects was conducted worldwide in the WPT, far-field WPT. So some milestones, the first is in 1975, the JPL and NASA, they demonstrate the very high efficiency wireless power transfer. So they demonstrate from one side the transmitter to the receiver Rectenna array, and they demonstrate the efficiency can up to 80%. So 80% efficiency transmit from convert from the electromagnetic waves into DC power. And from end to end, so overall efficiency reached to 54%. So means that you send like 1 volt from the transmitter, you can receive overall more than 0.5 volts at the end. So that is a pretty impressive value for the WPT. And also at the same year, they demonstrate the very long distance is is 1 mile path away, and very high power is up to 30 kilowatts wireless power transfer from one side to another. And later on, the Japanese did explore on the space of transmitting wireless power from the space to the Earth. Okay, and also the 2008, the longest WPT experiment conducted in the Hawaiian Islands. So the distance is 148 kilometers. So the WPT technology is particularly interesting for the locations with the remotely located, like the isolated islands. So the cable electricity is hard to reach. So the WPT is one solution for that kind of application. So now we come to today. So currently we have 2 directions of applying this technology. So one is the indoor application. Okay, it's over the air wireless charging. So that is the future. So like if we walk into a room, and so this device can charge your phone, charge your watch, or smart devices automatically. So that is the one direction of today's WPT application. So another one is outdoor, very long distance solar power satellites. So this is a very big project. Okay, it's actually being investigating in many countries in the world. So China is one, and Japan, and the US, and the EU. They all have similar kind of project. The point is to capture the solar energy in the space. So why we capture the solar energy in the space? Because the solar energy, the intensity is 6-fold more in the space than on the Earth. And also it's like 24/7. It's continuously. Okay, now the solar energy in our Earth, we can only use like half a day in most places. But in the space, the energy intensity is much higher, much higher. So the project is to capture the solar energy in space and transmit via the microwave to the ground and capture it and deliver to the electricity grid. So that is the plan, one plan by the project in China. And so they expect that by year 2050, the power level will reach gigawatts power level. So through this project, so it may solve our energy crisis we are facing today. So it's one like variable solution. So in the next, I would like to show you two small demo of the long distance like a solar power satellite system. So this is work done by the US Navy recently, very, very recent.
So the official name of this project is SCOPEM, which is this complicated acronym that stands for Safe and Continuous Power Beaming Microwave. What we're actually doing in the project can be stated in a bunch of similar terms. We've been tasked by the Pentagon to deliver 1 kilowatt of electrical power at a distance of 1 kilometer using a microwave beam.
The point of SCOPEM was to demonstrate wireless power beaming link at the microwave frequencies. So the component is, the components are we need a transmitter and we need a receiver to rectify the power. So the transmitter, we use a 100 kilowatt high power amplifier to amplify RF power going to a dish, which then focuses the power toward our Rectenna array. The Rectenna array we designed in-house to receive the RF power and convert that power to DC power.
The Rectenna is an array of tens of thousands of X-band antennas. Each of these antennas is connected to a small rectifier diode. That diode converts the incident microwave power into DC electrical power. Our experiments use a microwave source driving a dish antenna. Now, our dish antenna has this variable focus zoom feature to it that lets us focus the power at specific standoff distances from the transmit site. Then at the receive site, we have a Rectenna array. The Rectenna array converts the microwave beam to DC electrical power.
SCOPEM has been tested at 2 sites. One is in Blossom Point, Maryland, and the other is at MIT's Hoosier facility in Massachusetts. And we did testing at 2 sites for a few reasons. At Blossom Point, we were able to deliver a very large amount of power, 1.6 kilowatts, exceeding the target we had for power delivery by 60%. And at the site that we did in Massachusetts, we didn't have quite the same power level, but the average power received was much higher, which meant that we actually sent more energy with the demo we did in Massachusetts than in the one in Maryland. As you'll see in the footage, we could use that received energy to power up a big bank of bright LEDs for the Massachusetts demonstration, because the power beaming link at Blossom Point, Maryland, while being higher power, was on for a shorter period of time at a lower duty cycle. The total amount of energy transfer was smaller.
Power beaming is the efficient point-to-point transfer of electrical power across free space using a directive electromagnetic beam.
The link for SCOPEM was just over 1 kilometer, and the total amount of power was 1.6 kilowatts. We had been targeting 1 kilometer and 1 kilowatt, so we exceeded both of those goals easily. And the reason for setting those targets is to push this technology farther than has been demonstrated before. This is the most significant microwave power beaming demonstration that has occurred in nearly 50 years. And by setting these targets, we have exceeded all but one demonstration. One was done way back in 1975 with a huge dish at California. It's also facilitated with a very large receiver, both a much larger transmitter and a much larger receiver than we use here. So we've been able to approach that watermark with much smaller transmitter, much more receiver, and we it's a lot more sense for doing some of these
power beam, you want to use as high frequency as possible to keep the beam tight. But you don't want to use too high a frequency or you can start losing power to the atmosphere. It turns out 10 gigahertz is a great choice. 10 gigahertz, the component technology out there is cheap and mature. And even in things like heavy rainfall, the loss of power is less than 5%.
Benefit of using microwave power versus other frequencies, let's say millimeter wave or optical. One big one is if you want to wirelessly power from space to Earth, you get a lot less absorption in the atmosphere from microwaves compared to optical waves. And so for that use case of space to Earth power beaming, microwave is a huge benefit.
We learned that we can exploit scattering from terrain half the beam in order to increase power density at the target location. This should be really useful in future terrestrial applications for microwave power beaming.
This demonstration paves the way for power beaming on Earth, in space, and power beaming from space to the Earth.
Power beaming is the ultimate green technology. Unlike other sources of clean energy that we have on Earth, like TXLs and windmills, which provide intermittent and sporadic electrical power, power beaming from space to the Earth can provide power continuously, 24 hours a day, 7 days a week, 365 days a year. And that's something that no other form of clean energy can do today.
Microwave power beaming is definitely safe. There are limits that have been set by international standards bodies for what a safe power density is. And as engineers, we develop systems that will not exceed those safety limits. And that means that it's safe for birds, it's safe for animals, and for people in cases like we've done in the past with laser power beaming, where the power density might be higher, we can successfully implement interlock systems so that if something starts approaching the beam can shut off. We did not have to do that in this case because the power density was sufficiently low that it was intrinsically safe.
From the standpoint of technology readiness level, I feel that we're very close to demonstrating a system that we could truly deploy and use in UT applications.
Yeah, so this most recent demo just tells us the wireless power transfer from high power is viable and also the safe. And the most suitable frequency is 10 gigahertz, around 10 gigahertz microwave bands, because at that band is a less loss from the space to the Earth when the EM wave transmitted from the space to the Earth. So this is the huge project of the WPT. And if you look at the indoor application for the commercial, I can show you a very short video. It's called MiAirCharge technology. So charge your mobile devices over the air. So let's take a look.
What does charging look like in the future? Imagine walking into a room and your phone automatically begins charging. Today, we're bringing this closer to reality, introducing MiAirCharge technology. Using a system made up of 144 antennas, it transfers energy to the smart in the form of an extremely narrow millimeter wave beam. Within a few years, we offer a low charging solution. If you had a sensor, it also supports multi-device charging, charging with well-being, or even with some delay. Smart living will be truly this. This isn't science fiction. This is technology. MiAirCharge technology.
Yeah. As I said, it's not a scientific fiction, it's a technology. And many companies actually working on such system and nowadays. And we also have some startups like working on this. And one important thing is that the FCC, Federal Communication Committee, has already granted the application for the wireless power transfer at the world level at any distance. So from the government standpoint point of view, so it already have no obstacle to develop such product. So this is basically a short background introduction, and now let's move on what we targeted. So we targeted on the Internet of Things applications. The reason is that so the IoT applications have been developing really fast, and by the year 2028, the IoT global market value will be $17.1 trillion US, and the critical issue in current system is that all the IoT devices is powered by the chemical battery. So you have some major drawbacks. For example, short life and bulky, and it will create non-degradable rays. It's not green technology. And also it have the danger of explosion, in particular for the lithium-based batteries. So in some applications, for example, the forest fire prevention application, you cannot use such battery-based devices. And also in some applications, you need to, it's difficult to replace those batteries, and it's hard to get access by human beings. So in such conditions, wireless power transfer is only solution. So in the wireless power transfer system, we need two critical components. So one component is the wireless power transmitter that will deliver the power efficiently and smartly to the devices that need charging. But on the other side, we need a very compact wireless power capture device that can capture the power and convert it to the DC power efficiently. So our aim is to first develop the very compact, ultra thin, and high directive beam steering array. So why we need beam steering? We want the high directivity. So for antenna array, if you array have high directivity, you have a narrow beam, right? If you have narrow beam, that means the coverage is lower. So if you steer the beam, the purpose is to increase the coverage. So by using a linear array and with the beam steerable characteristics, we can steer the high directivity beam to achieve long distance communication and large area coverage simultaneously. So this is one of our targets. And another is very compact Rectenna to capture the power effectively. So this is the two systems. So as I mentioned before, we need to develop the very compact, high efficient, low cost Rectenna systems to capture the wireless power efficiently. The major challenge for antenna design is that you have a small antenna, that you have the low gain. So it's very difficult to design a very small antenna, but you maintain the gain, or even you design a super directivity antenna. So it's a trade-off. So what we do, this is the first design that we have developed. It's an electrically small Huygens linearly polarized rectangle. So the concept is a Huygens source concept. So it's similar with the ME dipole as Professor Tom and Professor Luke have developed before. So it's if you have a pair of orthogonal placed electric and magnetic dipoles, if they have the same amplitude and have the same phase, they have the two different vertical planes. So their electric fields have different shape. So for example, at the plane XOZ, at this plane, the E dipole will have the eight-shaped electric field, and with the electric field facing at this direction. But the magnetic dipole, however, will have the O-shaped pattern. So according to the superposition, they will add up at one side and cancel with each other, because electric field is the same direction at the upper direction, a positive Z direction, and they have the opposite at the negative Z direction. So which means that they will cancel each other at the back side, but add up at the front side. So the combined pattern will be a Huygens pattern like that. So it has many interesting characteristics, like very wide beam width, very wide beam means that it has very wide radiation coverage or radiation capture capability, and also the high front to back ratio. And the gain also stable compared with the conventional dipole antenna. So based on this concept, we developed the electric-small Huygens antenna. So which actually consist of two electrically small radiators. So one is the capacitively loaded loop CLL. So this yellow color, this loop is we call the CLL, which is the electric small radiator, works as the magnetic dipole. And then we placed a Egyptian X dipole beneath this CLL. So we excite them at the bottom, so the two radiators can be excited simultaneously with the same phase, but they have the orthogonal place orientation. So this one is the first, okay, in the literature, the first can realize very low profile, it's lambda over 25, and it's very small. The Ka is only 0.73. So Ka is the value that we define if antenna is electrically small. So if Ka is less than 1, the antenna can be defined as electrically small antenna. So this value is small, means that the antenna physical size is small, and the efficiency is high, and front back ratio is high, and realized gain is high. So this is actually the ideal candidate for the WPT applications. So if you look at the physics behind that, so if the two individual electric and magnetic dipoles, they have the omnidirectional radiation pattern, right? But if they combine like organically together, they produce the Huygens pattern like that. Okay, Huygens pattern like that. So we designed the system at the 950 micros. So it's a free M band, and with the Huygens pattern like that. So if we look at the current distribution, and we can find the Huygens radiation principle. So how the electric and magnetic radiators are associated with each other. So it's actually in phase and orthogonal. So we compare so our electric small antenna with the conventional dipole antenna. We can see, although we have a much smaller diameter, okay, much smaller, but this simulation in CST, so how the device is captured wireless power. So although we're smaller, but we have a much larger wireless power capture area. So this means we're smaller, but we are stronger. So that is a very the big improvement. And then later on, we need to integrate. So we only have antenna. Cannot do the wireless power transfer. We need to integrate with the with a highly efficient rectifier circuit. And then later on, we design a very highly efficient rectifier circuit. So by using the two dials and some matching components. And so first we developed the rectifier circuit itself, operating at 950 micros, and it realized the AC to DC efficiency around up to 80.3%. So it means that you have 1 volt power in and you get 0.8 DC power out. So this is a rectifier. And later on, we found that at this original rectifier, we need this matching inductor here. Actually, this matching inductor is very lossy because you know the inductor is made of the wires, right? Wires is in the microwave frequency quite lossy. And to integrate them together, we can design our antenna impedance to conjugately match the capacitive impedance of a rectifier circuit to get off the inductor. So we further increase the efficiency, overall efficiency of the system. The interesting feature of our antenna is that we change the impedance, but our radiation pattern is maintained the same. So it doesn't affect the radiation pattern. And so this is the whole system that we have built. And this is the measurement setup in the chamber. And we have demonstrated 89% AC to DC power conversion. So this is the first WPT rectangle we have developed. The very small is the smallest. We can claim the smallest in the world with such wireless power capture capability. And later on, based on the design, we also developed the dual functional by integrating the communication function as a rectangle function together, and by using the dual polarized characteristics. So they have the very high isolation of this Huygens antenna in the cross placement. They have a very high isolation. So we can use one. So both of the element can work independently. So we developed a system that can work as antenna and also rectangle together. And this is some of the measurement results. And then later on, we're considering the polarization. So if there's a linear polarization, it has a polarization mismatch problem. If the two systems, the transmitter and the receiver, are not aligned. But in most of the IoT applications, the orientation of the device is random, right? It's random. So in that system, circular polarized system is the much better solution. So first we developed the CP, Electrically-Small Huygens antenna system. So what we do is on the basic linear polarized system, we add another pair of electromagnetic dipoles, another pair, but excite them with 90-degree phase difference. So that is the concept to generate the circular polarization. So what we do is we have here the cross the formation, and we excite them with the cross short dipole to excite the system with the proper phase. And so we developed the CP antenna, so the circular polarized, and with the almost the similar characteristics. So just from CP, everything from the linear pole to the circular pole. Okay, so other characteristics remain the same. And later on, we applied the rectifier integrated with the CP system. Okay, with the CP system. Okay, so this is the first work because our first excitation techniques using the short dipole that must match to 50 ohm. And it's so if it's have to match to 50 ohm, we have to use this matching inductor here, so which is I introduced before, which is lossy. And so in total, we realized the efficiency at 80%. And later on, we invented a new excitation technique to manipulate the input impedance of the CP system to directly match the rectifier and avoid the lossy inductor. So we first developed the spiral feeding system. The spiral feeding system that gave up actually the capacitive impedance, because these have the parasitic capacitance between the feeding structure. And later on, we found that if we have a delay line structure like that, because a delay line would have the long wire, they're going to give us the more inductance. So this one actually can give us the inductive input impedance, but also generate the proper phase that's required to generate the CP system. So this is just the ideal one that we can get rid of the inductor. So we finally realized the 90% AC to DC conversion efficiency of this design. And so later on, and we found that actually, so the first one, we need 3 PCB disks. okay, to construct the whole system. And later on, we found actually everything can be printed on a single PCB. So the efficiency will be further increased, and the gain will be further increased. So this is the most recent design, and it's on the single PCB. The CLL is here, the EAD is here, the driven dipole is here. So everything is very simple, but it's very high efficient. So it gives us a Huygens pattern. And it's straightforwardly, we can integrate the rectifier circuits all together on the single PCB. So everything is low cost. And later on, we also integrated the photocell as light sensor to demonstrate the WPT-enabled light detecting system. So this system, how it works, so it's fully wirelessly powered. So when in dark environment, so if we attach the acoustic siren in dark environment, is no power, right? But in the dim or in the bright environment, the acoustic siren will be alarming. So I can show you a short demonstration how this works in the lab. This is a panel, electrically-small Huygens rectenna, which consists of an Egyptian X dipole, a capacitively loaded loop, and a highly efficient rectifier circuit. They all together were printed on the single piece of PCB substrate. This rectangle could be used to power up low-power IoT devices. Today, we are going to demonstrate a light alarming sensor, which is fully wireless powered by this rectangle. Let's see how it works. First, let's turn on the signal generator here. You could hear that the device is alarming. Let's say we turn off the lights. We could hear that alarming has gone. Let's say we turn on the lights again. The device is alarming again. This light sensor is fully wirelessly powered and very compact. This light sensor could be also replaced by other IoT devices, like the temperature sensor, humidity sensor, or even low-power transceiver to design fully wirelessly powered IoT devices. Yeah, so this short demo shows how this fully wireless powered system works. So in the future, we intend to integrate with other devices and also the supercapacitor to store the power. So it's a basic concept that how the wireless power transfer works. Actually, because of the Huygens pattern, it's very wide beam. Even we rotate this device like very high angle, we also receive the power efficiently because the beam is very wide. That's just one characteristics. Okay, so I just demonstrated the several wireless power capture devices, and we also developed the wireless power transmitting antenna array. So this one, so what we achieved is the linear antenna array, and with the beam scanning characteristics. One of the feature of the Huygens antenna is that when you scan the beam, because the single element have the very wide broad beam, if you expand it as an array, when it's scanning, the gain variation is very small. It's smaller than other kind of antenna. So here, you can say that the beam variation is very small, and if we numerically calculate, it's the same thing. So what we do in this work, we develop the theoretical calculation based on ideal Huygens source. So we calculated the radiation pattern as an antenna array and the beam scanning performance. So we found that when the Huygens elements expanded this array, it also have the wide beam width at one plane, at the vertical plane. If we look from the axis, so if here is the axis of array from the top, if we look from the top, we can see when the beam is scanning, their beam width at that direction is always very wide beam. So which means they have large coverage. So we also numerically demonstrated is wide band. So how a wide beam. So how we do? So first so for any antenna radiation work, we need to know the current. So the current is the basis of how antenna works. So we calculate the E current movements and the magnetic current movements, and we know the exact, so it's the ideal Huygens source. We have ideal Huygens source, we can calculate the E field in the far field. If we have the E field in far field, we can calculate the directivity from the total power and this Poynting vector. We can calculate the radiation pattern of the ideal Huygens source. And we put it into the array, so we can, we change the phase, we can calculate the beam steering performance. So this is the 9-element beam steering array. So this colored line is simulation. The dot line is the calculation. So we found that this, the calculation and simulation actually very agree with each other very well. So when the beam is scanned to like almost 45 degrees, so it's really very well. And so another interesting feature is that when the beam is scanned, the gain variation is less than 3 dB. It's very small. Even the beam is scanned to the 90 degree. It's very small. So later on, we realized the design with the prototype with a PCB-based prototype, and we developed a 3x3 button matrix to verify the concept. So the button matrix is actually a feed network at the 3 ports. So at each port, we excite at each port and terminate another 2, and we have the same amplitude output, but we have the different phase difference between each port. So by applying different ports, we can steer the beam. So it's a multi-beam antenna array. So this is a prototype, and this is some of the measurement and the simulation results. So the again agree with each other very well. So it's very simple. It's just one PCB, and low cost as well and highly efficient. So this is some summary of this work. So our work actually was had recognized like internationally, and which gave us confidence to continue to work on this area and to develop the wireless power transfer systems. So this is some research work on the wireless power transfer. So I will also take this opportunity to introduce some of our other research works. So we also did some space communications. So basically, it's designing CP antennas. Yeah, because the satellite communication, if you use a linear system, the linear wave passing the atmosphere, the polarization will change. So the CP doesn't have this issue. So we developed the different kinds of CP antennas for the geostationary satellite. So geostationary satellite means that satellite is stationary as respect to the Earth. So for some applications, we may use the conical beam. So if we put on the top of a car, if the car rotates, so the beam, if we have the conical beam like this, the beam can always point it to the satellite. So this is the geostationary. And in some other scenario, the satellite may be on top of us. For example, if we are in Singapore on the equator, so the satellite may be just on the top of us. So we need a broadside pattern like that. And so we developed a series of conical or broadside CP antennas, also omnidirectional antennas. So so this one is actually the conical beam CP antenna. Conical beam, so what we do is actually we use a pair of electric and magnetic dipoles, but place them parallel to each other. So like our Huygens design, they have a negative phase difference. But if we make the electric magnetic dipole parallel to each other, but have negative phase difference, they will give us the omnidirectional pattern. If we have a ground plane beneath, it will give us a conical beam. And this one is a quadrifilar helix antenna. So which is actually is quite wide used in the old time in the space. They have the helix antenna to generate the CP wave. So we developed so what we do here is we use the wideband feed network to excite the helix hydrophilic helix to make it wideband. Also, so this one is the reconfigurable CP antenna that can switch the polarization from the left-handed to the right-handed circular polarization. And we also make the magnetic conductive ground, AMC, artificial magnetic conductive ground, beneath that to lower the profile. So, and this is the omnidirectional high directivity CP antenna, which is all 3D printed. They have the high directivity and the omnidirectional, but with the C circular polarization. So this is the simplest design of this kind. And we also developed the wideband CP array and some beam switchable CP antenna. So this is all for the satellite communication. And so in my PhD, I also did some the biomedical applications. So to address the polarization mismatch issue in the body-centric wireless communication system. So we developed the implantable antenna, so which is a very simple PFA antenna, and put inside this is the muscle simulator liquid. So it simulated the human muscle structure, and we put this one in the liquid to do the experiments, and we developed a series of polarization reconfigurable antennas and to address the polarization mismatch issue in this application. And also we did some of the millimeter wave and the terahertz antennas. And this small one is the omnidirectional 28 GHz CP antenna. It's intended for the use as the mobile phone application. It's very small, so it's like only like 4 millimeter, so diameter, and working at 28 GHz, and can use for the device-to-device communication, device-to-device. And so this one is our recent work is still under review. So this is the high aperture efficiency antenna array. So we achieved almost 100% aperture efficiency. So I think it's highest in the world. So it's still under review. So this one. So what we do is it's also the Huygens concept. So we have the basic element of the Huygens one is coming from the rectangular waveguide. So each one is rectangular waveguide, and with the Johnson's this metallic plate, it works as an electric dipole. So we have an array of this. This one working at 28 GHz, 28 GHz. So all made by the full aluminum. So it's a full aluminum block, and it's achieved aperture efficiency up to 100%. So almost all the surface is contribute to the broadside radiation. And we also did some terahertz antenna. So this is a 320 GHz, so on-chip CP antenna, and realized by 0.13 by CMOS technology. So this intended for the space communication in the future. So basically, make a small conclusion. So our research work covers a lot of different varieties of applications. For example, the IoT, WPT application, the space communication, biomedical application, and millimeter wave and terahertz applications. So in the future, we have some targets. So first is the battery-free IoT sensing and communication system. that facilitated by the advanced Rectenna and also antenna arrays, and also the multifunctional intelligent antenna arrays to smartly deliver the wireless power to those the targets. And also the next generation wireless communication antenna in the circuit, in particular for the space communications. So this is the future perspective. Yeah, thanks very much. I think that's all.
Thank you, Wei.